Okay, so what does the mean value theorem state? All right, so it says that there is at least a one point between A and B where the derivative at that point is equal to the slope of the secant line, right, or the average rate of change. Or otherwise, what it indicates is that maybe I can draw a picture here. If the graph is like this, the black curve is f. There is some point, maybe around here, where if you draw a tangent, maybe it's this point here, f prime of c is the same thing. At c, the instantaneous rate of change at this point happens to be the same as the average rate of change between A and B. Okay, over here, maybe it's right here at this point, or maybe here, there may be 2 points here where the slope of the tangent line is parallel to the secant line. Okay, here's a more practical application. I hope you understand this. Let's say you're traveling. Okay, you're traveling, and at the 2-hour mark, you have traveled 100 miles away from the house, and 10 hours, so 8 hours later, between 2 and 10 hours after you left your home or something, you have found out you drive 660 miles. So within the last 8 hours, between 2 hours after your departure and 10 hours after your departure, in that interval of 8 hours, you have traveled 560 miles, right? From 100 to 660 miles. So it looks like you have traveled 560 miles in the last 8 hours, okay? And assuming that you drove smoothly, you didn't have an accident where the car stopped suddenly, or you just didn't have you didn't go do anything strange. You're driving, in a smooth way, differentiable way. Then at some point in the last 8 hours, your speed was exactly 70 miles an hour, which is 560 divided by 8. Okay, so at some point, if your average speed for the last 8 hours is 70 miles an hour, that means there was at least one point in time when your speed was exactly 70 miles an hour. Okay, so maybe it's around here, maybe it's around here. The slope, which stands for the speed or the velocity of your car, was exactly 70 miles an hour. Okay, so the question is, why the mean value theorem? It sounds so mean to come up with such a rigorously stated fact, okay, and the proof was hard. Why go through such hard work to prove what? Okay, and the answer, the first beautiful answer to that question is theorem 4.6 in the book. If f is differentiable, okay, in any open interval on any interval I, and if the derivative is 0 for all x on this interval, what do you think I can say? Right? So f is differentiable and the derivative is 0 constantly on an interval. Then you could probably fill in the rest of this. Then f is what kind of a function if the derivative is 0 everywhere? Right, it's constant on the entire interval. So if the derivative is 0, it can't possibly have any ups and downs. And you say, well, that's pretty obvious, right? It is obvious, okay? I mean, that is very easy to understand. It is very intuitive. But how do you know this is true, right? What happens? So then you start to argue, okay, if this is false, what would it mean? If not true, then that means it's not constant. So there's got to be a point above or below, right? So if there's any point on the interval, let's say if there's any points A, B on I such that f of A is not equal to f of B. Let's say f of A and f of B are different, okay? Then fb minus fa divided by b minus a. Oh yeah, so let's say A is to the left of B. A and B are different numbers, okay? A is less than B on this interval I. So you have this interval, and A is here, B is here. Let's say the values are different, okay? Whether FA is less than FB or vice versa. If they're different, then this difference quotient, FB minus FA over B minus A, cannot be 0 because the numerator is not 0 and the denominator is not 0 either, okay? So this can't possibly be 0, okay? Then, by the mean value theorem, there has to be a point C on AB such that the derivative of C is equal to this thing, which we know to be non-zero. But that's not possible because the assumption is that the derivative is always 0. Okay, so there's a contradiction. Now we have a great symbol for contradiction. That's this. Okay, it's like you're coming this way and you're coming this way and they have a head-on collision. See, that's a beautiful symbol, right? Okay, so this means this would be a contradiction. Now, why do we come up with a contradiction? The contradiction is we assume that there was any point A and B so that these two values are different. That was a contradiction. This assumption led to a contradiction, and therefore FA and FB are always equal to each other for all A, B on this interval. They can't possibly be different because if they were different, then the derivative at some point will not be equal to 0. See how important this mean value theorem was in proof of this. You could say, well, that's obvious, okay? I mean, this statement is obvious, and it is. But you can't just say this is obvious and therefore it must be true, at least not in mathematics. You can maybe say that in politics. You may even be able to say that in science because you can say, well, in 100 experiments, it always worked out that way. So we are sure it's going to work for the next 2,000 cases. No, we can't do that in mathematics, okay? In mathematics, we have to have rigorous proof, and you are seeing just a glimpse of that because, you know, we're not proving everything, but what we are seeing now in the middle of chapter 4, as we go through 4.4, is that sometimes for mathematics, in order to make a strong claim like this, right, you have to have a rigorously proved statement, which is a theorem. All right, so the Rolle's theorem gave us the mean value theorem, which now gave us this first statement, which says that if the derivative is 0 everywhere, then the function must be constant. All right, the next one, very similar, and it's a very natural step, that very natural next step, which is this: if f prime is equal to g prime for all x on an interval I, then g of x is simply a constant plus f of x. So in the our language, we say f and g differ only by a constant. Okay, now again, this is very easy to understand, I think, right? Because what happens is if the derivatives are the same, and if f looks like this, g must be parallel to that in order to have the same derivative everywhere. Okay, now the proof is pretty simple here. Consider f minus g as a function, which is fx minus gx. Okay, so f minus g, the derivative of this is equal to 0 for all x on I, since f prime is g prime for all x in I. That's given, right? And therefore, by theorem 4.7, sorry, you can't prove 4.7 by 4.7. By the previous theorem, if the derivative is 0 everywhere, that means f minus g is constant, say the constant c, okay, then fx is equal to gx. So I guess I should say, so you can say, yeah, I guess, I should have just wrote this differently. Let's say fx is equal to gx plus c, okay, because that's the way my proof came up with. All right, so they differ by constant. Let's say f is simply g plus c. It doesn't really matter which way, right? But the proof, since I wrote f minus g, the derivative is 0. That means f minus g is constant. Let's say the constant is c. So fx is equal to gx plus c for all x on this interval. Basically, all this is saying is that if the derivative is exactly the same everywhere for these two functions, then one function is a constant times plus another constant plus the function. F and g differ only by function, and they are parallel to each other, just like this picture shows. All right, so that's the theorem 4.7. Okay, a couple more. Section 4.8, this is the crucial one. This is probably the one that you are looking forward to having. Okay, this is critical. So I'll color it. In fact, I'll color more, maybe more. Okay, because the more I color, you probably feel this is really, really important. And it is, okay? This is the important theorem. This is the ultimate goal for proving the mean value theorem, okay? I need a little more space, so I'm giving me a few seconds to add or to append a page because I need one extra page for this. All right, so this theorem says if f is differentiable on an interval I, okay, and here's the first part. If the derivative is positive on, I guess I should say, for all or for every value x on this interval, then guess what? F is increasing on the interval. And that's where we started the conversation with in section 4.4, right? That's what we wanted to say. This is intuitive. This is easy to understand. That's what we would expect. Positive derivative certainly should indicate that the function is increasing, okay? But the thing is, if you try to prove it rigorously, you could not do that at the beginning of section 4.4, because to prove this, and we are going to do this in a moment, to prove this, we have to depend on the mean value theorem, which again, in turn, has to depend on Rolle's theorem. So only with this series of or sequence of proofs, things that are stated true or proved to be true, only after that can we make these statements and be confident, mathematically confident, that these are always going to be true. All right, so the first part says if the derivative is positive, then the function is increasing. Similarly, if the derivative is negative for all x on I, then f is decreasing on I. All right, so let's just do the proof of the first part because the second part is very similar. All right, suppose, now what does it mean for this to be increasing? Okay, now again, we have to go to the definition, right? What we have to show is that whenever you pick A, which is less than B, then f of A has to be less than or equal to f of B. That's what we mean by increasing. So the way to prove this is by, again, coming up with a contradiction, and the contradiction will be obtained if you suppose it's not increasing. So suppose f is not increasing, and we know exactly what it means because we have a clear and careful definition of this. Suppose f is not increasing on I. It means there is, or there are, A and B on I such that A is less than B, like this, and FA is less than F of B. No, that's not true. FA is greater than F of B if it's not increasing. Okay, now I'm not saying this is true for all A and B. I'm saying there's at least one pair of points A and B on the interval I so that F of A is actually greater than F of B. Okay, that's the only way for the F function F to be not increasing on I. Okay, increasing means for every pair AB where A is less than B, F of A is less than or equal to B, right? So the only way F is not increasing is to be able to find at least one pair of points A and B so that A is to the left of B and F of A is greater than B. But then what? Oops. But then what follows then? But then FB minus FA over B minus A, the difference quotient. Look, FB is less than F of A. F of A is bigger. All right, so this will be less than 0. It's a negative number. And by the mean value theorem, there is at least one point C on AB such that F prime of C is this number, which we just showed is negative. Okay, but that's a contradiction. Okay, this can't be, because we are told that F prime C is always positive, right? For part 1, FC is positive. In fact, we said that the assumption is that F prime is always positive for all X on an interval, including this point C. So with this contradiction, we know that our assumption at the beginning, the supposed part, is wrong. So therefore, F must be, so we must have been wrong here. So the answer is F must be increasing. Okay, so there can't be any possibility that A is less than B and FA can be strictly bigger than FB. FA must be less than or equal to F of B. F must be increasing on I. All right, now the second part is quite similar, and you can see that. Basically, all you have to do is we assume or we suppose F is not decreasing on I, which then means that there has to be points A and B. A is less than B, so that FA is less than F of B. And in this case, this will be positive, but that can't be because we assume that the derivative is negative everywhere. Okay, with that contradiction, we would prove that F is decreasing on I. Okay, so that is going to be the proof for the this all-important theorem. Basically, this theorem says the following. Okay, let's just summarize this. Okay, what does it say? If F is positive, if F prime is positive, that means the function is increasing, right? And you say, well, duh, we knew that. Yeah, you probably knew that at the beginning of section 4.4. Now we can say with confidence, with mathematical rigor, that this is true. And by the way, whenever I move this up like this, an arrow going up, that means increasing. Okay, and if F prime is negative, then F is decreasing, not increasing, decreasing. And the notation for decreasing is this. Okay, it's going down as you move from left to right. And the third, this is the first thing you learned, if the derivative is 0 everywhere, then F is constant. Okay, but again, we're not talking about increasing at a single point or decreasing at a single point or constant at a single point, because constant at the single point is obviously true at every point, right? So this is all happening on an interval. You have to have at least, some point A and some point B where you begin and end an interval. And within this interval, you can say the function is increasing if this is the case, decreasing if this is the case, or constant if that's the case. All right, now that we know these things, we are confident that we can make these claims, thanks to the mean value theorem, which owes its truthfulness to Rolle's theorem, which owes its truthfulness to the extreme value theorem. Okay, and only having established the series of these theorems can you make such a claim. All right, so that's it. Okay, I am not going to ask you for any proofs of these theorems. You should be familiar with the statements of these theorems as you move forward. Okay, great work.